In 7.3b, we're going to calculate probabilities involving a sample mean when the population is normal. So let's start here. Women's height. What is the probability that a randomly selected woman is taller than 66.5 inches given that she comes from this population? So she's coming from this population, which denotes to us it is normal with the mean in this standard deviation. So I'm going to jot this down as the mean, and this here is the standard deviation of our actual population. Well, to do the probability question, let's define the variable x. It's going to be the height of a randomly selected woman. Okay, from that, I'm just going to write, I want to find the probability that x is greater than 66.5 inches. Well, we're just taking it from this actual population here. So this is really a Chapter 2 question. Let's do confirm. We're going to say it is a normal distribution with the mean and the standard deviation as they stated. Really nothing to do. I'm going to show my calculator speak, the normal CDF of my lower bound and upper bound with mean and standard deviation, and there's my answer. So again, this is a Chapter 2 type of question and not a Chapter 7 one quite yet. Here's the difference between Chapter 2 and Chapter 7. It's this question here. What is the probability that the mean height of an SRS of 10 young women is greater than 66.5? So notice the difference. Before I do this, I actually need to now check the conditions to get the new mean and standard deviation. So to check the conditions, the first is random. They told us they took an SRS of 10 young women. SRS means simple random sample. We're good. Let's check the 10% condition. So for independence, the 10% condition is our population greater than or equal to 10 times the sample size. All I'm going to say here, as long as our population is greater than 100, we're good. Now, let's talk about, is it normal? Well, the normal condition on this is easy. The population is normal, so the distribution of x bar is normal. And we are good on that. So since I've checked the conditions, I'm actually going to get the various statistics that I need. Some key statistics, the sample size is 10. I have the current mean and standard deviation of the population. So based on that, I can compute mu of x bar. The mu of my sampling distribution, remember, is just the mean of my population, so it didn't change. The standard deviation of x bar is the standard deviation of my population, but I have to divide it by the square root of my sample size. So this is my new standard deviation. Now, if I wanted to see a graph of this, like I did in Chapter 2, I can do a quick sketch. Do notice the mean is just this right here. We want to know the probability that it's greater than 66.5, so this type of tail on the right-hand side. Now, this problem is different in that my variable isn't just x anymore. My variable is actually x bar. X bar is the average height of the SRS of 10 young women. Remember, they took a sample of 10 and they computed the mean. So the sample was 10 different x values, but then they took 10 different x values and computed the mean, so they got an x bar. So that's why we call it x bar. Okay, what do we want to find? The probability that x bar is greater than 66.5. That is that the mean of this sample is greater than that. Well, I have all of my parameters stated, and all I have to do is my calculator speak on this. Normal CDF, my lower bound and upper bound are right there. The mean and the standard deviation, be careful. We do want to make sure that you use the appropriate mean for that and the standard deviation. And then the answer from that is going to be 0.0057. So notice the difference in the probabilities between the first two questions. The first answer for just one woman was a 21% probability. This one, that we have a sample of 10 women, the probability is quite a bit lower, which should make sense. Let's look at this example of buying some peanuts. Here we have the Nutty Peanut Company. They do dry roasted shelled peanuts are placed in a jar by a machine. The distributed weights in the bottles are approximately normal. Okay, we know the population is normal. The mean is 16.1 ounces, standard deviation 0.15 ounces. So this is what we know about the population. Part A, without doing any calculations, explain which outcome is more likely. randomly selecting a single jar, finding the contents of a weight less than 16 ounces, or randomly selecting 10 jars and finding the average weight to weigh less than 16 ounces. Now, think about the variability. If we select 1 jar versus 10 jars, as the sample size increases from 1 to 10, who has less variability? In that case, since the averages are less variable than individual measurements, that is, our group of 10 versus our group of 1, I would expect the sample mean of 10 jars to be closer on average to the true mean of 16.1. Because the 10 jars are going to be closer to the average, it's more likely that the single jar is going to weigh less than the 16 ounces compared to the average of the 10 jars. Okay, now they actually want us to find the probability of both of those events we just talked about. Okay, we can do that. The first one, therefore, is let's randomly selecting a single jar and finding that the contents weigh less than 16 ounces. Let's define our x variable. Our x variable in this case is the weight of the contents of a randomly selected jar of peanuts. They have stated in the problem for us already that x is normal with our mean and standard deviation because we are just pulling this one jar. Remember, we're doing a single jar from the actual population. So this clarifies the mean and standard deviation and approximately normal. We want the probability is less than 16 ounces. So if the probability is less than 16 ounces, I'm going to do a normal CDF from my lower bound to my upper bound with the mean and standard deviation. And I get that the answer is 0.2525. So there's a 25% chance of getting a jar less than that. Now remember, we hypothesized that this one is going to have a higher probability than the 10 jars. So let's look at a sample of 10 jars. Now we're selecting the 10 jars. How do we do the problem differently? Well, we do have to check the conditions for random, independent, and normalcy because we want to compute a new mean and standard deviation. So it is random. They already told us that. The independence is our sample size. I'm going to do 10 times 10 already. There's at least 100 jars, so we can assume the independence. And it is approximately normal. We know that because the population is approximately normal. So we're guaranteed the sampling distribution will be. So now let's go in and define our variable in this case. The variable here is let x bar be the average weight of the 10 jars. Remember, we're going to take the 10 different jars, so each jar is an x, 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 x. Take all those x's and average them up. So based on that, we can go ahead and say x bar is a normal. Here's the new mean, here's the new standard deviation. We've clarified that enough. And then what is the probability x bar is less than 16? We're going to do our normal CDF. Careful, we are using the adjusted standard deviation. The probability here is about 1.75%. So we were definitely right in our initial assumption that it agrees with what we said. 1.75% is by far less likely than 25% is. It's worth looking at one last example here. So here we have 500 people attending an international conference. It was determined the average distance traveled by the conventioners was 1,917 miles, and the standard deviation was 2,500 miles. What's the probability that a random sample of 40 attendees, so that's my N, would travel the average distance of 900 or less to attend? Okay, let's talk about how to address this problem. I'm going to be a little more formal in the state, plan, do, and conclude. So for stating this, we want to find the probability that a random sample of 40 attendees to the convention traveled an average distance of 900 miles or less. That is, I want to find this right here is my scenario. What is the probability? The average of my 40s in the sample is less than 900. I want to define x bar. It's the average distance traveled of the SRS of 40 attendees. Okay, let's check the conditions. Random, independence, and normalcy. So on here, the 10% condition, if I check that first for independence, a sample size of 40 times 10, as long as we have 400 people attending this conference, we actually know there's 500. So in this one, we can actually be specific. Our population of 500 is clearly greater than 400. So yes, the independence or the 10% condition is met. Now let's address, can we do normalcy and the randomness in here? They did tell us that they took a random sample of 40, so the random condition is met. And for this case, the normalcy, it doesn't actually state it in this problem. This is just more of a typo on their part. Do know that this problem would say that this was normal in the initial problem. So because of that, I can actually say that our sampling distribution is also normal. So with that, let's go ahead and compute our new statistics. The mu for this one, the mean of our population in this case is 1,917. So our mu of x bar we assume is the same thing. The standard deviation, we do just have to adjust for our sample size. Standard deviation of our population is 2,500. Therefore, of our standard deviation of our x bar is going to be 395.28. To do the population computation here, I'm just going to do normal CDF. We want less than 900, so our lower bound and our upper bound, our mean and our new standard deviation here is going to give us a probability of 0.005. We can now make our conclusion and just say that the probability that a random sample of 40 attendees to the convention traveled an average distance of 900 miles or less is 0.005. It is very unlikely that the people coming to this convention are close by, is what it says. They traveled from afar more so to get here.